Hi, this is Dane Quinn from the University of Akron. Today's example will deal with planar kinematics. Here we have a bar of length L, half a meter, that's pinned at the ground at O and rotates. So if I tell you at this instant in time the angle theta is 20 degrees and theta dot, so the time rate change of that angle, is 2 radians per second, while theta double dot is minus 5 radians per second squared, I'd like to find the velocity and acceleration of a point P that is located out here at the end of the bar. So again, if I'm telling you everything about how this angle changes, I'd like to find the velocity and acceleration, or how the position of point P changes. We'll start with coordinates and directions. We'll define directions I and j fixed in the ground. Then we'll use directions E1 and E2 fixed in the bar. So E1 and E2 rotate as the bar rotates, and E1 in particular is inclined with respect to the horizontal direction I by this angle theta. So since these directions are fixed in the bar and they rotate with the angle theta, I can relate E1 and E2 back to I and j. So E1, for example, is cosine of theta in the I direction and sine of theta in the j direction, while E2 is minus sine theta I plus cosine of theta in the j direction. Also, I can write I and j in terms of E1 and E2. I, for example, is cosine of theta in the E1 direction minus sine of theta in the E2 direction, while j is sine of theta in the E1 direction plus cosine of theta in the E2 direction. If you notice, in the problem statement, I gave the angle 20 degrees also in terms of this angle phi. 2 radians per second I defined as omega, and minus 5 radians per second squared I defined as alpha. So I want to distinguish between the values of theta, theta dot, and theta double dot in general, and these specific values at this instant in time. So clearly, as this bar rotates, theta is not always equal to 20 degrees. It's only equal to 20 degrees at this instant. And so that number, that value, I'll refer to as phi. Likewise, there is an angular acceleration, so the angular velocity is not constant. So theta dot is not equal to 2 radians per second all the time. It's only equal to 2 radians per second at this instant in time. So again, I like to distinguish between the values of theta and theta dot and theta double dot at this instant, and the idea that these quantities are actually functions of time. These are just the values of those functions, again, at this instant. So at this instant, theta is equal to phi, and I can express the position of P with respect to O in terms of the direction E1. So that's going to be L. L is the length of the bar in the E1 direction. Likewise, the angular velocity of the bar is theta dot in the k direction in general, and at this instant it's equal to omega k. Finally, the angular acceleration of the bar is theta double dot in the k direction, and at this instant that is equal to alpha k. So again, alpha is minus 5, omega is 2, and the angle here is 20 degrees. So, since O and P are fixed in the bar, I can easily relate their velocities. The velocity of P, in particular, is equal to the velocity of O plus the angular velocity of the bar cross r of P with respect to O. And the equation that relates the accelerations of those 2 points is the acceleration of P is equal to the acceleration of O plus alpha, the angular acceleration of the bar, cross r of p with respect to O plus the angular velocity cross the angular velocity cross the position of p with respect to O. Now I need to take these expressions and substitute in the values that I know. So, looking at these two, the velocity of p is equal to the velocity of O, which is 0, O is fixed in the ground, plus the angular velocity, which at this instant is omega k, cross L E1. And so we can evaluate this. K cross E1 is E2. So the velocity of P is L omega in the E2 direction. And if I take the numerical values that I've been given, L and omega, then this becomes 1 meter per second in the E2 direction. So now turning to the acceleration of P is 0 because the acceleration of O is 0, it's fixed in the ground. The angular acceleration is alpha k cross LE1 plus omega k, the angular velocity, cross omega k cross LE1. And I can evaluate this now to find that the acceleration is, this term becomes minus L omega squared in the E1 direction. K cross E1 is E2, and then K cross E2 here is minus E1, plus L alpha E2. K cross E1 is E2. So again, using the numerical values that we were given, this becomes minus 2 meters per second squared in the E1 direction plus minus 2.5 meters per second squared in the E2 direction. And so we're able to find the velocity and acceleration fairly easily and fairly nicely in terms of the directions that are fixed in the bar, E1 and E2. So here I will note that this result is equivalent to polar coordinates, where instead of E1 we use ER. So if I just change E1 to ER and E2 to E theta, then we would find the same result. So these velocity and acceleration formulas can reduce down to polar coordinates when we choose the appropriate directions, but they are in fact a more general representation of the velocity of 2 points fixed in an object. However, they are a more general representation of velocity and acceleration of a point fixed in an object in terms of another point also fixed in the object. So now, if we're interested in the velocity and acceleration in terms of I and j, we can calculate that too. Remember that the velocity of p was L omega in the E2 direction. And if you recall, we have E2 written in terms of I and j, and we have E1 written in terms of I and j. So wherever we see an E1 or an E2, we can go in and substitute in that direction in terms of I and j. So this becomes L omega, and so at this instant, E2 is minus sine of phi in the I direction plus cosine of phi in the j direction, or grouping all this together, minus L omega sine of phi in the I direction plus L omega cosine of phi in the j direction. And so again, using our numerical values here, we find minus 0.342 meters per second in the I direction, plus 0.940, and I just used a calculator here to plug all this stuff in the J direction. So then, turning to the acceleration of P, remember, was minus L omega squared in the E1 direction, plus L alpha E2, or again, using our representation of E1 and E2 in terms of I and J, minus L omega squared times cosine of phi in the I direction plus sine of phi in the J direction, and then L alpha times E2, which is minus sine of phi I plus cosine of phi J. And again, we can group all these terms together. We'd have a term here and here in the I direction, and then here and here in the J direction. And finally, using calculator, we get the acceleration is minus 1.02 meters per second squared in the I direction, plus minus 3.03 meters per second squared in the J direction. Again, I just substituted in the numerical values that were given in the problem statement. So now if you look down here, I've actually written or drawn the position and velocity in this graph, and then I've drawn the velocity. Here it's a little smaller than over here just due to the scale, and the acceleration. So remember, the velocity is the change in position. So given this position vector, the velocity is L omega E2, which is here. L omega E2. Now, when we go to write that in terms of I and J, essentially what we're doing is just taking this vector and writing it in components in the I and J direction. Right? So this green vector is a component here and a component there. So this term is minus L omega sine of phi I. That's this vector here. And then this vector is L omega cosine of phi in the J direction. So again, we have the vector, and I can write it in terms of components in E1 and E2, and that becomes very easy because the velocity is just in the E2 direction. Or I can write this green vector in terms of components in the I and J direction. So now, looking at the acceleration, again, the acceleration is the change in velocity. So the velocity vector, and again here it's a little smaller just so I can fit the larger acceleration onto the page. These two vectors are actually exactly the same thing. So this vector is the change in the velocity. So looking at the acceleration, this purple vector has a component in the minus E1 direction. So that would actually be this component. And then it has a component in the E2 direction. Well, alpha was negative, so that ends up being in the minus E2 direction, like so. So this term is minus L omega E1, and this term is L alpha E2. Again, alpha was minus 5 in the problem statement, so we get a component in the minus E2 direction. But this expression in the I and J direction, well, it's exactly like before. So it's just the component in the I direction and the component in the J direction of this purple vector. This piece in the I direction is minus L omega squared cosine of phi minus L alpha sine of phi in the I direction. And this piece here, this component, is minus L omega squared sine of phi plus L alpha cosine of phi in the j direction. So these vectors, velocity and acceleration, can be expressed in terms of different sets of basis directions. So I can express them in terms of E1 and E2, like here and then here, or I can express them in terms of I and j. Right? So those are components in the horizontal and vertical directions. But either way I do it, it's the same vector. Right? This green vector is the velocity, regardless of how I choose to express it. And this purple vector is the acceleration, regardless of what directions I choose to express the components in terms of. So that's it for this example. We have, again, looked at an object that's fixed in the ground and rotating. Then we found the velocity and acceleration of a point that is located at the end of the bar. And we've talked a little bit about different sets of coordinates for expressing the velocity and acceleration. So that's it. Thanks so much, and I will talk to you again